Hi. Well, if you're ready, this will be the other big side of calculus. We still have two functions as before. Let me call them the height and the slope, y of x, and the slope s of x. Function 1 and function 2. That's what calculus is about. And earlier, we figured out how to go from function 1, if we knew that, how to find the slope. Of course, it was easy when function 1 was just a straight line, then the slope was just up divided by across. But when function 1 was curving, we had to do something. We had to take just a small distance across, a small distance up, and divide, and then let small get smaller and smaller. That was, the result of that was function 2, the derivative. Today, we're going the other way. We know the slope. We know s of x, and we want to find the height y of x of the graph. We know what how the graph is sloping at every point, and we have to put all that information together to find its height. Okay, let me say the easiest way to do it when it works is to recognize, if we're given a formula for the slope, to recognize maybe we know a height that goes with it. Let me take an example. So the one most important case of a height is x to some power, x to the nth. That's one that everybody learns. When y is x to the nth, the result of this process that produces function 2 going in that direction is dy dx is that n comes down and we have one lower power. So if we happen to have that as our slope, that would be our height. Nothing more to do. But many other slopes are possible. Let's just stay with this another minute. What if the slope was x to the nth itself? What if we started with function 2 as x to the nth? Suppose dy dx is x to the nth power, like x squared. Where does x squared come from? Well, look at this rule. That rule said that for these power functions, the power drops by 1. So if I want to end up with x to the nth, going backwards, function 1 had better involve an x to the n plus 1. But that's not perfect, of course, because when I take the slope of that one, this factor, this power, this exponent, n plus n, will come down. Just as n came down to here, n plus 1 will come down, and therefore I better divide by n plus 1, so that when I do take the slope, when I do go to number 2, the n plus 1s will cancel, the power will drop by 1, and I'll have x to the nth. Okay, there's an example, quite a useful one, of going from step 2 to step 1 just by kind of recognizing what you want there. So this is one set that everybody learns. Another is sines and cosines, if you can fit it into that. Another is e to the x or log x. That's pretty much the list. And then you learn in the future ways to change things around to fit into one of those forms. But then, of course, there are many, many cases, many, many functions too that you can't fit into a form where you can recognize from some list, which you either have learned, or you find on the web, or you find in the calculator. A lot of lists have been made to help you go from 2 to 1. But today we have to understand what is the actual process. What is the reverse process to this one? And of course this one involved a limit as delta x went to 0, because always I have to remember that things can be curving, things can be changing. I can't assume that they're staying the same. And then the reverse direction. Maybe I just tell you first what the symbol is. If I have this s of x and I want to get back to y of x, so this is from 2 to 1. 1 will be y of x. The symbol for y of x will be, I'm just really wanting to draw that integral symbol. The integral, I would say the integral of s of x dx. And you'll see why this is, so that's an s. You'll see why that's a reasonable way to write it. But of course, first we need the idea behind it. Okay, so how am I going to proceed? Step 1, I'll take steps. I won't try to get immediately to the case of continuous change. I'll take single individual steps. Let me do that. And then I'm going to take smaller steps. And then in the limit, I'm taking continuous steps. Okay, so first, big steps. So let me put down, for example, suppose I have y's. Suppose the y's stepped up like 1, 0, 1, 4, 9, 16, whatever. So those are heights. And of a graph that's sort of pieces of straight lines, only changing a few times. What would be the slopes? Going now, this is 1, going to 2, the slopes, s. Well, the slope, if the step size is 1 and I go up by 1, the slope will be 1. Here I go up by 3. Here I go up by 5. Here I go up by 7. So to go from there to there, I'm taking differences. I'm taking delta y's. These s's are delta y's. How do I go backwards? Suppose I gave you 1, 3, 5, 7. And I started y off at 0. How could you recover the rest of the y's? Well, that 1 plus 3 is the 4, 1 plus 3 plus 5 is the 9, 1 plus 3 adds 7 more, you're up to 16 and onwards. So if going this way is a subtraction at each step, going this way is a kind of running addition. I add up all the slopes to see how far I've climbed. Let me do a second example just to make that point. Let me start you, this time, let me start you with the slopes, because that's today's job. Suppose the slopes are 4, 3, 2, 1, 0. So if these were speeds, I would say, okay, I'm slowing down. I'm slowing down, but I'm still moving forward. Positive speeds, but putting the brakes on. What would be the distances if the trip meter start the trip meter at 0? Okay, then in the first second or hour, the first delta x, we would go 4. And what goes there? 7, right? I'm accumulating, adding up the distances. Here I was at 4, I went another 3 to 7, to 9, to 10. I didn't move, no speed, no 0 slope, stays flat. It's hit the top at 10. Okay. I could do this with any bunch of numbers, and I can do it with letters. So now I move from arithmetic to algebra. Algebra just means I'll do it with any letters, but I'm not yet doing it continuously, which is what calculus will do. Okay, so with letters, I have here y0, y1, y2, y3, y4, let's say. So those are the y's. Now what are the slopes between them if there's if the step across is 1? So that what are the steps upward? What are the delta y's? Well, y1 minus y0, y2 minus y1, y3 minus y2, y4 minus y3. And then my question is, these are the s's, these are the delta y's, you could say. These are the y's. What happens if I add all those delta y's? Do you see what happens? What happens if I add those 4 changes to get the total change? Well, when I add those, do you see that y1 will cancel minus y1, y2 will cancel minus y2, y3 will cancel minus y3. So the sum, can I use just a sigma symbol, but I'll just say sum and you know what I mean, of these delta y's is what? It's what happened after all those cancellations. Did everything cancel? No way. y4 is still there, minus y0 is still there. So it was y4 minus y0, the last y minus the first y. I'll just write y last minus y0, y first. Y end minus y start is the sum of the delta y's. Simple algebra. Reminding us again, though, and again, that the opposite, the inverse, to go the other way from 2 to 1, we add, where before we took, so we add pieces to get back to the y's. Okay. All right, this is looking, now I'm coming closer to what I want, but I'm moving toward calculus now. Okay, so calculus, I got there by delta y's over delta x's. So in moving toward calculus, what am I doing? I'm thinking of the changes delta y over smaller steps delta x. So it's really, I just want to take this step. I want to divide by delta x and multiply by delta x. Why do I do that? That's because it's this delta y over delta x that is the ratio, it's those ratios. Whatever the size of delta x is, and it's going to get smaller and smaller. I'm going to look at the change over very short steps. Then it's that ratio that makes sense. Delta y over delta x is a reasonable number. It's close to the s. It's close to dy dx, but it hasn't got there yet. I'm multiplying by the delta x, the small step that's going to 0 but hasn't got there yet. And I'm adding, and I get the last one minus the first one. Okay. Now, here comes the limiting step. So the limiting step will be the limit of this left-hand side, this sum. So in the limit, I'll have more and more and more things. How many, you see as delta x gets smaller, if I'm thinking of some fixed total change in x, I'm chopping it up into smaller and smaller pieces, more and more pieces. So more and more pieces of the slopes at different points along times the size of the piece give this answer. So now can I jump to the way that I would write this in the limit? In the limit as delta x, so now let delta x go to 0. And I ask the right-hand side, y last minus y first, is not changing. Y at the end, I'll write something different, y end minus y start, just to make that same point again. But it's this that's changing as delta x goes to 0. This becomes dy dx. But this sum becomes times the little delta x's are going to 0. Here's the way I write it. So in that limit, I can't legally write that sigma. So this integral symbol is was copied from that sigma, but it's telling you that a limit has happened. And in that limit, this is dy dx. And this, the notation, is dx. I've got what I predicted here with s of x there. So what I hope this discussion has, by starting with numbers, by going to algebra, by looking at the sum of those things, which was simple, and then by going to the limit, which was not simple. So a whole lot of limit has been not fully explained, and I think the right thing to do now is to do an example. So let me move to an example. Okay. So I'll take a particular function and follow this process, this limiting process, and see what it gives. And it will give us function 1, and as a bonus, it will give us a new meaning for function 1. Okay, let's do it. So now I'm going to take a particular s of x. So here's x. Let me take s of x to be 2 minus 2x. I didn't want to take one totally simple that I already had started the lecture with, but it's not difficult either. We'll be able to see what's happening here. Okay, so let me graph it, because I want to do this now with the graph. So x is, at x equal 1, s of x is dropped to 0, where at 0, when x was 0, it started at 2. So it started somewhere here. Here was 1, it's halfway down. It's going to come down in a straight line. And let me stop there. It could continue, but let me call y end is going to be 0, and y start is going to be, we'll see about that, sorry. S at the end is 0. S at the end is 0. I don't yet know what y at the end is. It's not 0. Okay, so what's my idea? Well, not mine. Newton and Leibniz and a lot of people had these ideas. It's kind of interesting. So Archimedes, he goes way, way back before Newton, Leibniz, or anybody conceived of them. Archimedes figured out how to deal with a curve with a parabola. Archimedes got from a parabola, he got from x squared, the parabola, back to a height. by special ideas. He didn't see, he was one of the great mathematicians of all time, but even Archimedes didn't see what you now see, this connection between function 1 and function 2. If he had seen that, he would have gone further. All right, now let's see it. What I'm now going to try to do is go through, I'll take a delta x equal, let me take a delta x equal to a quarter. So this is delta x here, and this one is 2 delta x's, and this one is 3 delta x's, and the one is 4 delta x's in my original delta x, which is a quarter, which is small, but not really small. Okay, so now what do I do? All right, look at this first period. The slope, the s function, function 2. See, over here is going to be function 1. This is going to be the y, the integral of that. But I don't know what it is yet, so it's pretty open to question. Okay, so now let's get there. So the point is that over this interval, the slope is changing. It's changing a significant amount, not too much, but it's changing. And I don't know, from the algebra, I don't know how to deal with that. So I'm going to take the start, I'm just going to take a value within this, some value, and stay with it within that interval, and I'll take the starting value. So over this first delta x, I'm going to pretend that the slope stays at 2. So I'm pretending that this is my slope function. And then over my next delta x, I'm going to pretend that it stays at that's probably 1.5. And then I'm going to pretend that it stays at 1, and then I'm going to pretend that it stays at 0.5. Okay. Right? It's like, if you allow me to go back to distance and speed, I'm chopping up the full time, the day, let's say, into 4 pieces. And in each piece, the speed is changing, which I'm not ready to deal with, which algebra isn't ready to deal with. So the best I could do was say, okay, suppose the speed is constant at what it was at the start of that short time. So those would be delta t's rather than delta x's. The s would be representing speed, but no difference in the picture. Okay, so now let me do these things. So I'm taking s. Now I'm going to do this addition, which won't give me exactly the right y, because those rectangles are not exactly right. But I'll get them better by taking smaller delta x's. Let me see, what do I have here? Okay, over this first time, I have my slope, which I'm taking to be 2. So that's the delta y over delta x. That's the s. And the times the delta x. And then, and what is that? We might as well just face it, that 2 times that delta x, we can think of that as the area in that tall, thin rectangle. Well, I've introduced the word area for the first time. It never showed up on the previous board. It's the extra insight that's coming today. Okay, now over the second short period, I'm going to fix my speed at 1.5. 1.5 times delta x, because my speed, I'm setting at 1.5, and this is how long I go. So this is a distance, or a change in height, a change in y. And you see what's coming. The next one will be a 1 times the delta x, and the last one will be a half times the delta x. Okay? Yeah. This is adding the way I did in the algebra. Okay. And what do I get? Well, this, again, is the area of that piece. This one is the area of that piece. This one is the area of that piece. I get an overestimate because the true slopes had dropped a little within each piece. Okay, I get some quantity which I can figure out, but it's not the right answer. It's not the final answer. And what is now the main step to get there? Chop delta x into half, you could say. Why not cut it in half? Now I'll have a different picture. Can you see what this picture is doing? Now, over the first little half of the old step, I am up here, but then I drop to here. Do you see that a little, can I do this with an eraser? A little bit got chopped away, a little bit got chopped away. Where is it gone? I'm going to have this zigzag is, that wasn't too bad. That's now, so I'm replacing that with sum of 8 pieces, because delta x is now down to 1/8. You see that the number of pieces, this is what we said about that sum. That sum is got more and more terms because it has a term for every little delta x. And the size of that term is about like delta x multiplied by an s. So what I'm getting in the limit is a kind of running sum, a running counter, a mileage meter, a trip mileage that's adding up distance based on speed. And what I'm getting, now do you see what I'm getting in the graph picture? What happens to the shaded part as delta x gets smaller and smaller? The shaded part is going to be the curve, these little wrong pieces are going to get reduced, and in the end, the total height at 1 is going to be, this is the moment, the area under the slope curve. This y turns out to be the area under the s of x curve, or line. Okay, so at x equal 1, what is it? What's the area out to 1? Okay, well, we've got a triangle there. Its base is 1. Its height is 2. Area of a triangle is half the base times the height, so I have half times 1 times 2. I've got 1. The y at the end, the area at the end is 1. But, oh, I shouldn't say but, I should let you applaud first. But, no, but. What if I only went that far, halfway? What if that was Sn? What if I want to know what is y at x equal a half? Then it'll be just, of course, just the area up to that point. Can I remove this part of the picture for a moment? I'm always looking at area. And the area of that, do we know what that area would be? It's not a triangle anymore, it's some kind of a trapezoid. As delta x goes to 0, I'm going to get the correct area, which will be what? Let's see, I have a half as the base, and the average height is about 1.5. Can I do that little calculation? The base is 1/2, and the average height is 1.5. I think I get 3/4. So halfway along, it's got up to 3/4. Where is 3/4? So this is 1, this is 3/4, this is 1/2, this is 1/4. So at 1, it's at 3/4. Oh no, it's halfway along. Yeah, halfway along, it's at 3/4. Okay. I would like to know that graph now. I'm ready to jump to the limit. And let me do it the way I said at the very start of the lecture. Let me take this and try to guess. So what? Taking a shortcut. Because do we go through this horrible process every time we want to do an integral? Of course we don't. The best way is, can we find a y function, a function 1, that has that derivative? Let's just try it. I'm allowed to take it in 2 pieces. That's a very valuable fact. So what has the derivative 2? If the slope is 2, what's the function? If the speed is 2, what's the distance? It's constant speed 2 times the total distance. The slope of the 2x line is 2. Clear. What about the 2x? What has the slope? Which function has the slope 2x? Well, we saw it over here. The function that has the slope 2x is x squared. Because when I take the slope of x squared, the 2 comes down. I have the 2, so the 2 shows up. I have 1 smaller power, x to the first power. This is the correct y, and I hope that my graph gets those points right. At x equal to 1, this is 2 minus 1. This is the correct height 1. At x equal to, what was that? That was 1/2. All right, here's the moment of truth. Now set x equal 1/2, and what do you get for this y? You get 2 times 1/2, that's 1, minus 1/2 squared, 1/4. Hey, miracle, 3/4. This area I figured to be 3/4, and this approach also gave 3/4. Either way, multiplying those is 3/4, subtracting those is 3/4. So my graph, what does my graph look like? What does the graph of that look like? Its slope at the start, what's the slope at the start? The slope at the start is s at the start. And s at the start, when x is 0, the slope is 2. So it starts out with a slope of 2. But it's slowing down. It's like this, a little bit like this one, where s was, the car was slowing down. We're not picking up distance so quickly. We're not picking up height so quickly. But we're still going forward. We're still picking up some height. So it starts with a slope of 2, bends around to there. And I guess maybe that is, yes. That's almost, picture's almost good, but not great. So the slope is 2, and there. And what is the slope at this point? You can't tell from my picture, which isn't like perfect. The slope, I'm told what it is. When x is 1, the slope is 2 minus 2. Slope 0. The slope is 0. We're not picking up any more height, any more area. And of course, that's right. When, at this point, we're not picking up more area. If I continue beyond here, we're losing area, because below the axis, I'll count as negative area. Just because, if it was speed, I'd be going backwards. That's what will happen here. I'll start down. So that, if that continued, this would still be the correct thing to graph. If I do graph it, that's actually the top at x equal 1, and then it starts down, and probably by, I don't know where, x equals something, maybe by x equal 2, oh yeah, you can see, by x equal to 2, it's got down to 0 again. When x is 2, this is now 0, and you can see that when x is 2, we'll have the bad area, the car going backwards, will be identical to the forward area. Total area is 0, and I'll be at this point when x is 2. Okay. Let me just recap a moment. Today was about going from function 2 back to function 1. The quickest way to do it is to find a function 1 that gives that function 2, and then you're in. But if you can't do that, or if you want to understand what the real behind it limiting process is, it's like the algebra, but it's this expression here that's concealing so much mathematics. Delta x going to 0, these ratios going to the actual function, and the delta x I replaced by the symbol dx indicating an infinitesimal. We'll see it more. Thank you.
This has been a production of MIT OpenCourseware and Gilbert Strang. Funding for this video was provided by the Lord Foundation. To help OCW continue to provide free and open access to MIT courses, please make a donation at ocw.mit.edu/donate.